Jupiter was supposed to be predictable, a giant ball of gas. Stable. Understood. But new data suggests something deeper is happening, and it's making scientists uneasy. Jupiter dominates the solar system in a way no other planet does. It is not merely the largest world orbiting the Sun. It is a gravitational authority whose presence shapes the architecture of everything around it. With more than twice the mass of all the other planets combined, Jupiter acts less like a participant and more like a regulator. Its immense gravity pulls, bends, and organizes matter across vast distances, influencing objects that drift millions of kilometers away. In many ways, the solar system does not simply include Jupiter. It is structured around it. Its gravitational pull is strong enough to sculpt entire regions of space. The asteroid belt between Mars and Jupiter exists partly because Jupiter's gravity prevented those rocky fragments from forming into a planet. Instead of allowing matter to gather peacefully, Jupiter's influence stirred it, disrupted it, and locked it into a permanent state of fragmentation. What might have become another world instead became a scattered field of debris, all because of one planet's mass and position. Comets traveling from the distant edges of the solar system often encounter Jupiter long before they approach the inner planets. Some are captured, some are redirected, and some are slingshot into new trajectories. In 1994, humanity witnessed Comet Shoemaker-Levy 9 collide with Jupiter, leaving scars larger than Earth itself. It was a dramatic reminder that Jupiter absorbs impacts that might otherwise threaten the inner solar system. Yet at the same time, simulations suggest Jupiter can also send objects inward, acting as both shield and unpredictable force. Beyond visible objects, Jupiter subtly influences orbital stability across enormous distances. The long-term balance of planetary paths, including Earth's, is partially shaped by Jupiter's gravitational rhythm. Its presence helps maintain order, but it also introduces complexity. Remove Jupiter, and the solar system's architecture might look entirely different. Add more mass to it, and the consequences could be catastrophic. It is a delicate balance governed by a single giant. For decades, scientists believed Jupiter's internal structure was relatively straightforward. It was described as a massive ball of gas with a possible compact core at its center. The assumption was that beneath its colorful clouds lay layers of hydrogen and helium arranged in predictable ways. It was enormous, yes, but conceptually simple, a scaled-up version of known planetary physics. That belief stood largely unchallenged for years. Then Juno arrived. When NASA's Juno spacecraft entered orbit around Jupiter in 2016, it began sending back data that complicated everything. Instead of a neat, well-defined core, measurements suggested something far stranger. A diluted, blurred interior where heavy elements are mixed into deep layers rather than confined to a solid center. Jupiter's core may not be a solid sphere at all, but a partially dissolved structure extending far deeper than expected. The giant was not simple. It was complex and dynamic. Juno also revealed that Jupiter's magnetic field is far more irregular than previously thought. Instead of a smooth, evenly distributed magnetosphere, the planet exhibits intense magnetic patches and unexpected asymmetries. These findings suggest powerful internal movements, possibly tied to vast oceans of metallic hydrogen under crushing pressure. Hydrogen, forced into a liquid metal state, conducts electricity and generates a magnetic field of staggering strength, the largest planetary magnetic structure in the solar system. Even Jupiter's gravity field turned out to be uneven in subtle ways. Juno detected variations indicating that massive atmospheric bands extend thousands of kilometers deep into the planet. The colorful stripes visible from Earth are not shallow surface patterns. They are rooted in deep flows that may reach far below the clouds. Jupiter is not a static gas shell. It is a layered system of moving energy, driven from the inside out. The deeper scientists look, the more Jupiter appears less like a simple planet and more like a massive engine of gravitational and electromagnetic influence. Its storms, radiation belts, magnetic chaos, and internal mixing reveal a world still evolving. The giant that once seemed predictable now challenges models of planetary formation and structure. Juno did not simplify Jupiter. It exposed its hidden complexity. And that is what makes Jupiter truly extraordinary. It does not merely orbit the Sun. It orchestrates the motion of countless objects around it. It protects, disrupts, shapes, and stabilizes. It is both guardian and wild card, architect and enigma. The solar system is not a collection of equal worlds. It is a system profoundly shaped by one dominant force. And the more we study Jupiter, the clearer it becomes. We are only beginning to understand the planet that controls everything. When Juno began mapping Jupiter's gravity field with extraordinary precision, scientists expected confirmation of long-standing models, a dense, compact core buried beneath layers of hydrogen and helium. Instead, the data revealed something deeply unsettling. The gravitational measurements didn't match a simple, well-defined center. They suggested something far more complex, as if the core itself was not neatly contained, but spread out, mixed, and partially dissolved into the surrounding layers. Jupiter's heart was not what we thought it was. Rather than a solid, sharply defined core, the evidence pointed to what researchers call a diluted core. Heavy elements that should have been concentrated in the center appear to be dispersed across a vast region deep inside the planet. It is as if the boundary between core and envelope was blurred. Not clean, not stable, not intact. This challenges decades of planetary formation theory, which assumed that giant planets form around solid cores that remain distinct even as they accumulate gas. One explanation is dramatic. Early in its history, Jupiter may have suffered a titanic collision with a massive protoplanet, perhaps 10 times the mass of Earth. Such an impact would not have been a surface-level event. It would have penetrated deep into Jupiter's interior, injecting energy so intense that it could partially disrupt or mix the core with surrounding layers. The result would be a planet permanently altered from the inside out. If this happened, the collision must have occurred during Jupiter's early formation, when the solar system was still chaotic and violent. In that era, planetary embryos were colliding, merging, and scattering. A massive impactor striking Jupiter would not simply bounce off. It would plunge inward, transferring heat and momentum on a scale almost impossible to imagine. The energy released would blur internal boundaries, reshaping the planet's structure before it fully stabilized. This possibility changes Jupiter's story completely. Instead of being a quiet, orderly gas giant that grew steadily around a compact seed, Jupiter may be the survivor of a catastrophic event. Its diluted core could be a scar, not visible on the surface, but written into its gravity field. If true, Jupiter carries the memory of an ancient collision hidden beneath its clouds, and the implications extend far beyond one planet. Jupiter has long been considered the prototype for gas giants across the universe. Thousands of exoplanets discovered around other stars resemble Jupiter in size and composition. If Jupiter's core is not solid and compact, then perhaps our assumptions about all giant planets need revision. The standard model may be incomplete. Planet formation theories often rely on the idea that a massive solid core forms first, then rapidly accretes gas. But if cores can be disrupted, diluted, or partially mixed, the internal diversity of giant planets may be far greater than expected. Some may have intact cores. Others may have blurred interiors. Some may have undergone violent impacts that permanently change their internal chemistry and structure. Juno's findings also raise new questions about how heat moves inside Jupiter. A diluted core could affect convection patterns, magnetic field generation, and long-term thermal evolution. The internal mixing of heavy elements might influence how energy escapes, how metallic hydrogen behaves, and how Jupiter's powerful magnetic field is sustained. The structure is not just a curiosity, it affects everything. The most unsettling part is how much remains unknown. Juno's data suggest mixing, but not the exact mechanism. Was it truly a massive collision? Or did gradual internal processes redistribute heavy elements over billions of years? Scientists are still debating. Each new dataset refines the picture, but also introduces more complexity. Jupiter is no longer a solved problem. If Jupiter's core is diluted because of an ancient catastrophe, then the solar system we inhabit was shaped by more violence than we imagined. The giant that stabilizes planetary orbits may itself be a survivor of chaos. And if that is true, then every gas giant in the galaxy may carry a similar hidden history. Silent evidence that even the largest worlds can be reshaped by forces powerful enough to blur their very foundations. Jupiter's magnetic field is the largest planetary magnetic structure in the solar system. It stretches millions of kilometers into space, forming a magnetosphere so vast that, if it were visible from Earth, it would appear larger than the moon in our sky. For decades, scientists assumed that such a powerful field would at least follow predictable symmetry, strong, centered, and relatively balanced around the planet's rotation. But when detailed measurements arrived, that expectation began to collapse. The problem is not its size. The problem is its shape. Jupiter's magnetic field is not evenly distributed. Instead of forming a smooth dipole like a bar magnet, certain regions are dramatically stronger than others. One area in particular, known informally as the Great Blue Spot, exhibits magnetic intensity far beyond what standard models predicted. This asymmetry suggests that the internal electrical currents generating the field are not flowing in neat, uniform patterns. Magnetic fields are created by motion. Inside Jupiter, extreme pressures transform hydrogen into a metallic state, a fluid capable of conducting electricity. As this liquid metallic hydrogen moves and churns, it generates powerful electrical currents. Those currents produce the magnetic field. But if the field is uneven, it means the internal flows of this metallic ocean are uneven as well. Something inside Jupiter is circulating in ways scientists did not anticipate. Traditional models assumed relatively smooth convection patterns deep inside the planet. Heat rising from the interior was expected to drive large, organized currents within the metallic hydrogen layer. Yet the magnetic irregularities imply more complex motion, perhaps layered convection, differential rotation, or localized turbulent flows. Instead of a simple internal dynamo, Jupiter may have a chaotic, multi-layered electrical engine. The discovery forces scientists to reconsider how Jupiter's interior is structured. If the metallic hydrogen layer is not behaving uniformly, perhaps its thickness varies from place to place. Perhaps heavy elements mixed into the interior, possibly from an ancient collision, are altering the flow of material. A diluted core could be influencing convection patterns, creating asymmetries in how electrical currents form and evolve over time. Even more intriguing is the possibility that Jupiter's magnetic field is still changing. Magnetic fields are not static. They evolve as internal flows shift. On Earth, the magnetic field drifts and occasionally flips polarity over geological timescales. On Jupiter, with its enormous size and extreme pressures, those changes could follow entirely different rules. The asymmetry detected today may not look the same millions of years from now. Juno's close passes over Jupiter's poles revealed magnetic complexity far greater than expected. Instead of a tidy structure, scientists found clusters of intense magnetic anomalies. This suggests that multiple dynamo regions may exist inside the planet, not just one deep global engine, but possibly layered or regional sources contributing to the overall field. If true, Jupiter's magnetic system is far more intricate than a simple rotating conductor. This complexity has consequences beyond pure theory. Jupiter's magnetosphere traps intense radiation, creating hazardous zones that can damage spacecraft. Understanding how the magnetic field behaves helps scientists predict radiation patterns and design future missions. But the irregular field also means that radiation belts may shift or vary in ways not fully understood, making Jupiter an even more challenging environment to explore. The deeper implication is that Jupiter's interior may not be fully settled. Although the planet formed over 4.5 billion years ago, its internal layers may still be slowly adjusting. Heat continues to escape. Metallic hydrogen continues to move. Heavy elements may still be redistributing. Jupiter is not a frozen relic of early solar system history. It is an active, evolving system hidden beneath clouds. The magnetic field problem reminds us that even the largest planet in our solar system refuses to fit neatly into our models. Its enormous magnetism is not just powerful, it is uneven, dynamic, and possibly still transforming. And if Jupiter's internal engine is more unpredictable than we thought, then our understanding of giant planets everywhere must expand to match the complexity of the giant that continues to surprise us. The Great Red Spot has been raging for more than 3 centuries, making it the longest-lasting storm ever observed in the solar system. Larger than Earth at the time of its earliest recorded measurements, it has dominated Jupiter's southern hemisphere like a planetary scar. For generations, it seemed almost eternal, a permanent feature carved into swirling clouds. But recent observations have revealed something unexpected. The storm is shrinking. Over the past century, and especially in the last few decades, the Great Red Spot has steadily decreased in width. What was once wide enough to swallow 3 Earths side by side can now engulf only one. The reduction has not been subtle. Astronomers tracking its dimensions have documented a clear, measurable contraction. Yet even as it narrows horizontally, something else is happening. The storm appears to be growing taller. Measurements from spacecraft and telescopic analysis suggest that as the Great Red Spot shrinks in diameter, it may be extending higher into Jupiter's atmosphere. This vertical stretching is unusual. On Earth, storms typically weaken as they lose energy and shrink. But Jupiter does not behave like Earth. The lack of a solid surface, the immense atmospheric depth, and the powerful internal heat flows create conditions unlike anything on our planet. Why would a storm contract in size but intensify vertically? One possibility is that the surrounding atmospheric currents are changing. Jupiter's atmosphere is organized into powerful jet streams that move in alternating directions at hundreds of kilometers per hour. If those jets shift slightly in strength or position, they could compress the Great Red Spot laterally while forcing energy upward, reshaping its structure rather than destroying it. Another possibility points deeper, beneath the visible clouds. Jupiter radiates more heat than it receives from the Sun, meaning its interior remains thermally active. That internal energy drives convection currents rising through the atmosphere. If the heat flux beneath the Great Red Spot fluctuates, it could alter how energy feeds the storm. A slight change in the internal engine might ripple upward, reshaping the vortex from below. Some scientists speculate that the storm may be shedding energy through smaller vortices. Observations have shown fragments peeling off the Great Red Spot's outer edges, smaller storms that break away like pieces of a larger system. This could mean the storm is gradually losing angular momentum, redistributing its power across Jupiter's turbulent atmosphere. But whether this process signals decline or transformation remains uncertain. What makes the situation more mysterious is that the Great Red Spot has already survived countless atmospheric changes. For over 350 years, it has endured shifts in surrounding jet streams and internal heat flows. If it is shrinking now, does that mean Jupiter's atmosphere is entering a new phase? Or is this simply part of a natural long-term cycle that we are only now witnessing? The vertical growth adds another layer of complexity. A taller storm suggests deeper atmospheric roots or stronger updrafts. It may be tapping into layers previously less influential. On Earth, height often correlates with storm intensity. But Jupiter's atmospheric chemistry and pressure gradients operate under entirely different physics. A shrinking footprint does not necessarily mean weakening. There is also the possibility that the Great Red Spot is evolving rather than fading. Jupiter's atmosphere is dynamic, filled with storms that appear and disappear over years or decades. Perhaps the red spot is transitioning into a new form, smaller in area, but more concentrated in energy. It could become a tighter, faster vortex rather than a sprawling giant. For now, scientists don't know whether the Great Red Spot is dying, transforming, or stabilizing into a new configuration. Its contraction challenges assumptions about its permanence. Its vertical growth complicates predictions about its future. The storm that once seemed eternal is changing before our eyes, reminding us that even on a planet defined by extremes, nothing remains frozen in time. If you're fascinated by space mysteries and discoveries that challenge science, subscribe now. Because what Jupiter reveals next could reshape planetary physics. Jupiter's radiation belts turned out to be far more intense than scientists originally anticipated. Before spacecraft ever approached the planet, models predicted strong radiation, but within limits engineers believed they could manage. Once probes began transmitting real data, those expectations were shattered. Measurements showed particle energies and densities exceeding safety margins, forcing mission planners to rethink shielding, trajectories, and operational timelines. Jupiter was not just hazardous. It was brutally extreme. The source of this radiation lies within Jupiter's enormous magnetosphere. Charged particles, mainly electrons and ions, become trapped by the planet's powerful magnetic field. As they spiral along magnetic lines, they accelerate to near-relativistic speeds, forming radiation belts that dwarf Earth's Van Allen belts in both scale and intensity. Any spacecraft venturing too close without proper protection risks permanent damage from high-energy particle bombardment. During the planning of the Juno mission, engineers faced a sobering reality. Standard shielding would not be enough. Sensitive electronics had to be placed inside a specially designed titanium vault to survive the harsh environment. Even then, the spacecraft's orbit was carefully calculated to minimize prolonged exposure. The radiation levels were not theoretical inconveniences. They were mission-threatening obstacles. But why is Jupiter's radiation so extreme compared to other planets? The answer begins deep beneath the clouds. Under immense pressure, hydrogen inside Jupiter transitions into a metallic state. This liquid metallic hydrogen behaves like an electrical conductor, capable of sustaining vast electrical currents. As Jupiter rotates, completing a full spin in under 10 hours, these currents generate an extraordinarily powerful magnetic field. This metallic hydrogen layer acts like a colossal dynamo. The rapid rotation of the planet amplifies the effect, intensifying magnetic field generation. The stronger the magnetic field, the more efficiently it traps and accelerates charged particles. Solar wind particles and material ejected from Jupiter's volcanic moon Io become captured, energized, and confined within the magnetosphere. The result is a radiation environment unlike anything else in the solar system. Io plays a critical role in this process. Its constant volcanic activity ejects sulfur and oxygen ions into space, feeding Jupiter's magnetosphere with fresh material. Once trapped, these particles are accelerated to extreme energies. The interaction between Io's plasma torus and Jupiter's magnetic field creates a complex, dynamic system, one that continuously replenishes and intensifies the radiation belts. The asymmetry of Jupiter's magnetic field also contributes to the unpredictability of its radiation zones. Certain regions are far stronger than models predicted, leading to localized areas of extreme particle concentration. This uneven magnetic architecture means that radiation exposure can vary dramatically depending on position. It's not just strong, it's irregular and dynamic. The radiation belts are so powerful that they emit detectable radio waves. Jupiter essentially broadcasts its magnetic violence across space. These emissions were first detected decades ago, but modern measurements reveal far greater complexity in how those emissions fluctuate. The radiation environment is not static. It pulses, shifts, and responds to changes in both solar wind pressure and internal magnetic dynamics. The deeper implication is that Jupiter's interior is not quiet. The metallic hydrogen dynamo continues to operate with immense efficiency, sustaining magnetic power billions of years after the planet formed. That persistent internal motion fuels the radiation belts and maintains Jupiter's dominance as the most magnetically intense planet in the solar system. The radiation is not a surface phenomenon. It is a symptom of a powerful, active interior engine. Jupiter's radiation belts remind us that this giant is not merely large, it is energetically formidable. Its internal layers generate forces capable of reshaping surrounding space, trapping particles, and creating environments lethal to unprotected technology. The metallic hydrogen deep within the planet acts like a hidden reactor, powering a magnetosphere so immense and violent that it redefines what we consider extreme in planetary physics. For decades, Jupiter has been described as Earth's great protector. Its enormous gravity acts like a cosmic shield, capturing or deflecting comets and asteroids that might otherwise travel toward the inner solar system. The dramatic impact of Comet Shoemaker-Levy 9 in 1994 reinforced this image. Humanity watched as fragments of a comet slammed into Jupiter, leaving scars larger than Earth itself. It felt like proof that the giant planet absorbs blows that might have been aimed at us. The logic seems straightforward. With its immense mass, Jupiter dominates gravitational interactions in the outer solar system. Many long-period comets entering from distant regions encounter Jupiter first. Some are captured into shorter orbits. Others are flung entirely out of the solar system. In this view, Jupiter reduces the number of dangerous objects that could cross Earth's path. A guardian stationed at the gates. But the story is not that simple. Computer simulations modeling the early solar system and long-term orbital dynamics reveal something more complicated. Jupiter's gravity does not only remove threats, it can also redirect them inward. When a comet passes near Jupiter, the interaction can alter its trajectory dramatically. Instead of ejecting the object outward, certain gravitational encounters can sling it toward the inner planets, including Earth. This dual role has sparked intense scientific debate. Is Jupiter primarily a shield, reducing impact risk over geological timescales? Or does it increase the flux of certain types of objects into the inner solar system? The answer appears to depend on the type of small body being studied. For some asteroid populations, Jupiter may stabilize or clear their orbits. For certain long-period comets, however, it may increase the chance of Earth-crossing paths. The situation becomes even more complex when we consider resonance effects. Jupiter's gravitational influence shapes the asteroid belt through orbital resonances, regions where gravitational nudges accumulate over time. These resonances can destabilize asteroids, gradually shifting them into new orbits. Some of those orbits intersect with Earth's. In this way, Jupiter indirectly contributes to the movement of material inward. Over billions of years, Jupiter has likely both reduced and increased impact risks at different times. During the early solar system, its massive gravity may have accelerated the clearing of debris, helping stabilize planetary orbits. But in doing so, it may also have sent waves of material inward, contributing to heavy bombardment phases that shape the surfaces of Earth and the Moon. What makes Jupiter's influence so difficult to categorize is that gravity is not moral, it is mechanical. It does not decide to protect or endanger. It simply follows the laws of motion. The same gravitational slingshot that ejects one comet into deep space can redirect another toward the Sun. A slight difference in angle or speed changes the outcome entirely. Some researchers argue that without Jupiter, Earth might face more frequent long-period comet impacts. Others suggest that a smaller Jupiter, or one positioned differently, might actually reduce certain types of threats. The protective narrative is appealing, but nature rarely fits into simple categories of guardian or villain. Jupiter's presence reshapes the entire architecture of the solar system in ways that are neither purely beneficial nor purely harmful. The deeper realization is that Earth's history is intertwined with Jupiter's gravitational dominance. The conditions that allowed life to evolve here may have been influenced by the giant planet's ability to stabilize certain orbital patterns while simultaneously delivering volatile materials through redirected impacts. Jupiter may have both shielded and seeded the inner solar system. Protector or risk? The truth is more nuanced. Jupiter is a gravitational architect, reshaping trajectories across millions of kilometers. Its influence is complex, dynamic, and sometimes unpredictable. The same force that shields us from distant threats could, under the right circumstances, send danger our way. And that complexity is precisely what makes Jupiter not just the largest planet in our solar system, but one of the most consequential. The real concern surrounding Jupiter is not a single anomaly, nor one surprising discovery. It is the pattern. Each time new data arrives, from gravity measurements, magnetic mapping, atmospheric analysis, or radiation studies, it reveals deviations from what scientists expected. Not minor corrections, but structural adjustments to long-standing models. The issue is not that Jupiter is mysterious. The issue is that it keeps proving us wrong in ways that force deeper revisions. For decades, planetary science operated with relatively stable frameworks for how gas giants form and behave. A solid core, layered hydrogen and helium, predictable convection, and a mostly symmetrical magnetic field. These were the baseline assumptions. Jupiter was supposed to be the template, the standard, the reference point for interpreting giant planets across the galaxy. Instead, it has become the exception to its own rules. Gravity data suggested a diluted core. Magnetic readings revealed asymmetry. Atmospheric observations showed storms behaving in unexpected ways. Radiation belts exceeded predictions. None of these discoveries alone are catastrophic to theory. But taken together, they reveal something unsettling. Our models were incomplete. And not by a small margin. Unpredictability is what troubles scientists most. Predictability is the backbone of physics. When equations consistently forecast behavior, confidence grows. But when the largest planet in our solar system resists tidy explanation, it signals that our understanding of planetary interiors, magnetism, and atmospheric dynamics may lack critical variables. Jupiter is not violating physics, it is exposing gaps in how we apply it. The concern extends beyond Jupiter itself. Gas giants are among the most common types of planets discovered around other stars. Many exoplanets resemble Jupiter in size and mass. If our primary example in our own system behaves in ways we didn't anticipate, then extrapolating models to distant worlds becomes more uncertain. Jupiter was supposed to simplify exoplanet interpretation. Instead, it complicates it. There is also the matter of scale. Jupiter is not a minor body whose anomalies can be dismissed as local quirks. It holds more than twice the mass of all other planets combined. It influences orbital stability, asteroid dynamics, and long-term planetary architecture. If our understanding of such a dominant object is still evolving, then our understanding of solar system history itself may need refinement. Scientific progress thrives on surprises, but repeated structural surprises raise deeper questions. How many other assumptions remain untested? How many planetary models are built on simplifications that work well enough until better data arrives? Jupiter's deviations remind researchers that even well-established frameworks can be provisional. This unpredictability also affects mission design. Future probes rely on models to estimate radiation exposure, atmospheric entry conditions, and magnetic field strength. If those models underpredict extremes, spacecraft risk failure. In that sense, unpredictability is not merely philosophical. It is practical and costly. Jupiter demands humility from engineers as much as from theorists. Perhaps the most profound implication is epistemological. If we misunderstand the internal behavior of a planet we can observe closely with advanced spacecraft, what might we be misunderstanding about distant systems light years away? Astronomy often depends on indirect measurement. If our baseline reference object resists full comprehension, then caution must accompany every broader conclusion. Jupiter's unpredictability is not a failure of science. It is a reminder of its ongoing nature. Theories evolve, models refine, but the larger lesson is this. When the most massive planet in our solar system defies expectation again and again, it suggests that the universe still operates with layers of complexity we have yet to fully grasp. And if Jupiter continues to surprise us, it forces a deeper, more humbling question. What else, across the vastness of space, are we still only beginning to understand? Jupiter is not collapsing. It's not exploding, but it is more complicated than we thought. A giant planet still surprising scientists after centuries of study. Subscribe for more cinematic space mysteries. Because sometimes, the most powerful worlds are also the least understood.